Yeah, that's worth mentioning. If you guys are interested in this stuff and want to see what happens, because the really frustrating truth of the situation is we've only been able to talk about planets, and it's a little crazy to talk about planets without talking about stars. And the entire next semester is built around stars. And so this course is honestly best taken together, but I know that your guys' requirements don't really incentivize you to take of these kind of courses. So almost nobody ever does. So it's a real terrible catch 22. But yeah, like Andrew pointed out, I always post lectures on YouTube on that same channel. So if you're interested in how stars work, you can check it out there. Right. But yeah, I mean, we're closing down things. I brought us to the edge of the solar system more or less. We could talk about trans-Neptune objects, but they're basically moon-like little rocky thingies. And yeah, we've been to them even less than we've been to everything that we talked about so far. And now it's probably getting close for us to put a concerted story on the whole project of where solar systems come from. And there's a couple possibilities with that. But before we do that, any thoughts or anything rolling around in your head after the last class? Yeah,
Not specifically from the last class,
sure.
but from the Trans-Neptunian Objects workshop.
Yeah.
The Oort cloud is substantially larger than I expected its
Hmm.
scale
Hmm.
to like the Kuiper Belt. It is so much bigger.
It is. Yeah. It's also like entirely theoretical too,
Hmm.
which is quite interesting. It sort of emerged out of a need for there to be a reservoir for comets, which is kind of interesting. But yeah, it's way far out there. It's really big. You can almost think about it as being darn near to the edge of the next solar system, which is pretty crazy. But yeah, there's very little to say about the Oort cloud other than maybe it's there and maybe that's interesting. We also now have interstellar comets. I don't know if you guys noticed.
Oh yeah,
That's now a
it's not
thing.
aliens.
What's that?
It's not aliens.
I mean, maybe it's aliens. It'd be strange to build a spaceship out of a giant piece of nickel, though. Um,
Could be aliens.
yeah, I guess so. It would be fun. Aliens are fun until they wipe out your civilization. Um,
Predicates with us defining life, then we can determine what's an alien.
yeah, there you go.
It's alive out there.
There you go. But yeah, we have all these comets. There's quite a few now. Well, there's three. It's not quite a few, but when I was in college, there was no such thing as an interstellar object. Obviously, there's probably, in so much as three have happened in the last 10 years, there's probably interstellar objects passing through our solar system all the time, since ever, which, to follow up on something I was talking about at the end of class last time, the dating of rocks and the fact that we've never found a rock that is dated older than 4 billion years, that gets a little bit more perplexing if you think about the fact that interstellar objects have probably been coming in here for a really long time, right? So it would be hard to believe that at least some of the stuff found on the surface of the Earth isn't interstellar in nature, I suppose, given enough time. Again, three of these things have flown through our solar system in the last 10 years. So, presumably millions of them have flown through in the course of the Earth, even if the Earth is only 4 billion years old.
And we've observed three of them.
That's what I mean. Yeah.
Could be 3,000 of them.
Yeah, yeah. It's probably quite common, I guess, is the answer. Yeah. So then you have to ask yourself, wait, so all interstellar, first of all, so none of the materials we find in asteroids and stuff, um, they're all from our solar system, and none of them have come interstellar. That's probably unlikely. Um, so why is all this material only dating to 4 billion years? Well, it might be a sort of metric problem with the fact that we're kind of measuring some sort of melt process or something that's much more complex than simply the date of these rocks. So I think that's an interesting piece of the puzzle as these interstellar things. Last time I talked to Avi Loeb, he's the guy who's kind of been championing the alien angle on this. I've talked to him several times, and last time I talked to him, I said he was going out to the Pacific to dig up one of these interstellar objects out of the bottom of the ocean. And I was like, how old do you think that thing's going to date to be if you do find it, right? Because, it's a fair question. I mean, how old would you guys expect it to be?
older than 4 billion.
Yeah, right? I mean, at least it'd be kind of weird if it was the same age as everything in our solar system. Like maybe, but that just seems like yeah,
I think that would be a useful piece of information if it did date the same age as everything else.
that's what I said too. I
Like
was like either way would be
out
interesting.
somewhere.
Yeah, yeah. So it's like if it is exactly the same age, then something's going on with this dating metric for sure, in my opinion. And if it isn't, then that'll be fascinating too, because you know, it would be the oldest thing that we'd ever dated, perhaps. If it was only 2 billion years old, that'd be even crazier too. So I don't know. This is all sort of wrapped up, and now we have comets to expect from other places than the Oort cloud. Yeah.
Um, Something that I was when I was looking into the stuff for my final project was uh, the fact that the only rocks we've been able to confidently date are the ones on the Earth and Moon because they're the only ones we've actually gotten physical samples back to Earth. We
Mm-hmm.
haven't
Mm-hmm.
even gotten the samples from Mars back yet, and we probably won't for a couple more decades.
Now, there's a couple of meteorites that are found, right, that people think are
Yeah,
from Mars,
yeah.
because but yeah,
But
maybe.
then, like, if we found a sample, decades or centuries in the future that was like on, say, Europa, that could date to like 6 billion years in the past, and then now that we'd have to throw out everything.
Yeah, I don't think we'd throw out everything though. People would just be like, okay, well, the solar system takes a little bit longer than we thought, or something like that. Um, I don't know. I think it'd be really fascinating if we did find a really, really old chunk of something around here. But your point is super valid. We have very few samples, and the ones on Earth that are really old, even ones that are older than 3 billion years, could be counted on one hand. So it's hard. It's hard to make up a story, and I think that's kind of what we're circling around is that we have to tell a story for this solar system, and the one we've been telling seems inadequate in the face of the story that we're seeing from exosolar systems. And so reconciling those two pieces of the puzzle is probably what the future looks like.
I think my biggest hang up throughout the entirety of this course, with everything that we've covered so far, is according to the standard story, the answer to most of the big questions, how the earth was formed, how the moon, all of the variations and the rotational axes of these kind of further out giants, whatever, whether they're gas or icy, is always something big hidden.
Mm, mm.
And yet, the way that we talk about the formation of the solar system and the way that we've talked about it so far, there doesn't seem to be any sort of actor or reason for something to, like, how did these bodies, what was the reason that they collided? What was the change? What was the action
Yeah,
that
yeah.
facilitated that?
Yeah, so I've kind of done a poor job of summarizing the mainstream position on the formation of the solar system. So I want to walk you guys through that today briefly before we kind of compare the possibilities. So that's the first thing I want to do is start in the 1700s, talk about the way that people are thinking about it, talk about all the deviations they tried on and why they came back to the original idea. Because they did try on a lot of different interactive models and stuff. So we'll look at that briefly. Um, but yeah, you have to fit all these weird pieces together, and I think that the level, what's kind of most exciting right now from our last conversation is that you're starting to see in these exosolar systems that there's a metamorphic dimension to all of these stories that's starting to emerge. And what I mean by metamorphic is that these planets are changing from one type into the next. I don't think that anybody would have ever been able to, let alone predict that, but also believe that it would be a super common process. But it's not like these hot Jupiters with their evaporating atmospheres are rare in other solar systems. They're actually the norm. They're super common, it seems like. So not only is planetary metamorphosis possible, seems to be pretty much what happens out there. But that those same ideas haven't been applied to our solar system at this point in time. And why is that? Yeah, Dante.
Probably has something to do with the conflicts of the I was I was looking into because my project is about the formation of different theories for the formation of the moon, and there's also solar system stuff in there too, and a lot of it was along the different theories held by different scientists were often held along the same borders as the Great Christian Schism,
Hmm.
which is interesting. And I point it out because the idea that the Catholic Church and the Orthodox Church have about how the world was formed is very different.
Hmm.
Uh, one, I forget which one is which, but I know one of them is more like everything was just perfect. It was built in the exact way that it is now. And the other one is everything was hodgepodge together and through coincidences and a whole line of, one is basically supernatural. It was just made in the way it is. And the other one is he essentially plucked things in different random orders to
Hmm.
hopefully make something as close to this as he could,
Okay.
right?
This was back during the schism, like in the Holy Roman Empire and all that stuff?
Yeah,
Okay.
between the Byzantines and all that.
Yeah.
And all the way to in the Enlightenment era and then now, there's just the cultural ideas of how the world was formed. One, people is more comfortable with, say, an eternal universe or metamorphic planets or a solar system that's not where planets are not like didn't just form in place, and one is not. Even if they're not religious, like a lot of the secular like ideas that even exist in America fundamentally come from the Christian beliefs of people who came here. And so it's odd, but that's one of the major reasons for that is it's culturally they have a harder like we brought up earlier in the course. Um, how would you feel if the universe was eternal?
Yeah.
Would you like if there was no beginning?
Yeah.
And culturally, you know, I have a hard time imagining that, but that's kind of
Half of people do, it turns out. Yeah. It's funny because half the people have a hard time not imagining that. Or at least like people in scientific circles that I run into. It's like, I think there's just a metaphysical divide, which is kind of what you're pointing at. It's like,
yeah.
you know, my wife always, she's kind of redefined the word metaphysics, I think, more robustly. I like her definition eventually, but she basically means the sort of preconceived beliefs that you bring to an argument in the first place. It's like sort of your set of assumptions that you go into a discussion space with. I guess my question is more, why is it that we look at all these solar systems, we see these hot Jupiters, we see metamorphosizing planets, but we don't apply that same logic to our own solar system? I think there's like just a very simple answer to it, actually. Yeah.
Because we have life and other solar systems don't. So we
Maybe they do, though. I think everybody's really hopeful. I'm thinking of something a lot more just kind of boring. Yeah.
We're stuck in convention.
I think that that's part of the culture thing Dante's talking about. That is true to some extent. We've gotten really comfortable with the story that we have. Yeah. But I think there's a really, really, I've said this before too a million times. We're not, but you got an idea?
I was gonna say, is it because our idea for our timeline is only 4 billion years?
Yeah. Yeah. So the idea is that with all of these extra solar systems, when I talk to astronomers, planetary scientists, astronomers, all these people, they always say stuff like, in the future, it will be impossible to determine if we visit a rocky world, a billion years from now, it will be impossible to say whether this Earth-like planet used to be at the heart of a giant Neptune. But that could have never happened for our solar system because our solar system's only been around for 4 billion years. That's not enough time for all of these things to have happened, basically, right? So the cosmological horizon that we place, this fundamental metaphysical assumption space that we have, where the universe is very, very young, right? I know that 14 billion years seems like a long time to you guys who are like 20-something years old, but it's very, very short geologically, especially if you consider the Earth is like, what, a third of that age on this scale. And these metamorphic processes that people imagine are transforming planets, they take billions of years, presumably, unless they're deeply catastrophic, in which case now you have to explain how your planet got moved close to the sun, burned off its atmosphere, moved away, survived. Like there's these huge stepwise transformations that don't fit neatly into this gradualism, this uniformitarianism. So I don't know. I find this all quite fascinating. What do we want to wrap last time's discussion to? I mean, hopefully you guys are seeing that there's essentially three types of planets, right? So we have terrestrials, right? Like the one we're standing on, all the rocky things with very thin or non-existent atmospheres. Then we have the giant planets, the icy ones and the gassy ones that, they're both quite liquid actually. Um, and really the story for astronomers, for planetary scientists, is to tell a cohesive story when we look at these other solar systems and hopefully look back at our own about how you get all these different shapes. And I really like to think about this in terms of evolution. That's why I titled this course The Evolution of the Solar System, because I think that ultimately we can learn a ton. And that's why I even bother talking about origins of life and things like that in this course. It's because in some sense, this is the perennial problem. Like this is what people were arguing about when it comes to life. How is it that some creatures look like dogs and some creatures look like humans? And then some creatures look like apes, which kind of look like humans, but not as much like dogs. And how do you put all of these things together on a tree or something so that you can come up with a rational story for how everything ended up looking the way it does, right? And the early models of the solar system, which I'm about to dive into, they didn't really approach the appearances so much on a tree-like fashion. Really, each planet is sort of given its own story that relates to how it formed inside of the system. Whereas with something like the evolution of life, we think about it as there's a simple organism, and the simple organism evolves complexity, and the environment specifies how it develops, and basically, we relate all life forms to one another through their ancestral paths, ultimately, right? And so the relatedness can be understood as being branches off of some common trunk. And I like that a lot. I honestly find it quite appealing in terms of explaining the appearances of most well, let's just stick with planets. I think that it's an interesting approach to explaining planets as well. So, let's Well, first of all, make sure anybody has any questions about what we did last time before we move on. But what I want to do today is ultimately look at the standard story, how it's evolved over the last 300 years and come back to itself. And then I want to compare that story to something that's a little more evolutionary and a little more metamorphic and see what it would take to reconcile the two. And then we have to talk a tiny bit about stars, maybe just to preview what we're going to get into. But since none of you will probably be here next semester, we can mention where stars fit into this metamorphic. You're going to be here? Oh, heck yeah. You're going to be here too? Awesome. That's really fun. All right, I won't give away too much then.
I'll watch it on YouTube.
You watch it on YouTube? Heck yeah. Awesome.
Just kind of,
Yeah.
there's an anecdote. I want to call it an anecdote because I don't have any context for how true or accurate
Yeah, that's fine.
the story is. But
Yeah, let's play with it.
there is a story that I heard about the evolution of paleontology.
Mm.
It was this sort of crisis moment because they had begun the speciation of all of these different forms that they had found.
Okay.
All of these different shapes and sizes.
Like labeling them and stuff.
Labeling
Yeah.
them, saying this is a species, this is a species.
Sure.
And there came this sort of tipping point when there was a realization made that the speciation had gotten out of whack because they assumed that all of the remains that they had found were adults.
Mm.
And they didn't account for the fact that there were like a growth cycle completely ignoring.
That's a really good point. Yeah.
If you like, there's it's kind of analogous to what you were saying, how initially every planet was given its own character, and it is itself.
Yeah, yeah, it has an identity. Yeah,
An identity.
yeah.
Right?
They do all look quite different. I hope you guys have at least gotten that much, right?
But
Like our Rockies even are so different from
like
each
we were
other.
talking about with the mushrooms, just because things look different,
Yeah,
the same,
yeah.
doesn't mean that they share any kind of.
No, it's terribly confusing.
It's probably the same mechanical process that's creating all of these things. So how are they just different because they look different?
Yeah.
Right.
Well, welcome to the world of theory, guys. There's no answers, it turns out. It's just whether something makes more or less sense to you. Yeah. Yeah.
It's all kind of like interconnected.
Yeah.
So like genetically they may be different and they look different.
Mm.
They have different properties, but at the same time it's like they are
The community. Yeah. Yeah.
connected. They all
Yeah. I mean, a forest is an insane creature if you think about it. The way that there's a whole economy between the root system and the mycelium, and they're exchanging nutrients for, safe harbor. It's just unbelievably complex. Yeah, I mean, I'm sure the solar systems are like that to some extent too. Like the complexity is in some sense never ending. But yeah, to your point, I often think like if, our civilization goes belly up, solar flare, I don't know what, and then 10,000 years from now, they dig up like Danny DeVito and Shaquille O'Neal,
Yeah.
right? They're going to be like, oh, there was lots of different types of hominids here back then, right? So, yeah, whenever you're trying to piece together the past, I mean, it's not a hopeless endeavor, but you should have some humility about whatever story I pin on this is probably incomplete to some degree, right? And I might have to update my story quite a bit. But I almost certainly will have to update it a little bit when I learn more about what's happening. And I don't know. I mean, again, metaphysical divide. Some people find that to be super exciting. I, for one, do. But other people find it to be threatening to their sense of a place in the world or something like that. And so, yeah, I hope that it's not unsettling to you guys. Uh, but I do think that, as humans, we have come to tell some pretty good stories about our past, despite the fact that we can never know 100% for sure whether they're true. It seems like the story that was being told in the 1800s that the Earth was, 6,000 years old is probably not tenable. It's not as tenable as it being 4 billion years old. I mean, with 4 billion years, you have a little bit of a better shot at explaining the diversity of geological forms, the sedimentary layers, all the different crazy creatures and dinosaurs, and you have a better shot at it. Maybe in the future we'll see the Earth as being far, far older than 4 billion years. Maybe timescales that we're completely uncomfortable with, like orders of magnitude times that time scale, will become completely fine. I mean, if you think about, one sec, Dante, I'll get to you in 1 second. If you think about how going from 6,000 years to, let's say going from 4,000 years, which is more or less on the order of what they thought, to 4 billion years, right? That's 6 orders of magnitude change. If we went from 6 orders of magnitude from 4 billion, we would be in thousands of trillions of years to make, like, that's the kind of change that happened essentially overnight in terms of the history of the world. So, crazier things have happened, and it would really rewrite our situation if we started considering those kinds of timescales. Yeah.
Only for the Catholics. I say that specifically because part of what caused the Great Schism
Mm.
was the discovery by the Catholic Church in the 13th century of the Talmud, which was because the Christian Old Testament, or the Catholic one, is only the first scroll of the Jewish Bible. And the last 2 scrolls have been lost or hidden for centuries. We don't know what happened to them during the Dark Ages. And when
Interesting.
it was found, the Pope ordered all of them to be burned. All of it. Because it was heresy. It completely destroyed most of the ideas they had about the Earth being 6,000 years old. Because there's one part of it, the whole, what we would call now, what Christians call book, a whole section that is literally just about time and how time to the Lord, time to Adonai is unfathomable to you. When we describe a day, remember that the sun and moon had not yet been created by the fourth until the fourth day. So then, how could days be happening if days are sun and moon? It's because days are not the same for you and the Lord. Is basically the idea, and so that and so modern day young Earth creationism, the idea that the Earth is only 6,000 years old or whatnot, is also stems from a similar thing
Sure.
because the during the Renaissance
That was super popular not that long ago, though. So that's what's crazy. Yeah.
they rediscovered that.
Yeah.
Basically,
I see.
There are
that
fundamentalists who believe that
Oh,
6,000 years too.
Yeah.
yeah, I had one in my class last semester. I mean,
Absolutely.
it's real for sure.
What I mean is that like it's this culture divide you speak of between the world being unfoundly old and not that old has existed since antiquity.
Yeah,
And
I could see that.
it has been rediscovered. This constant thing of it's actually really old.
Yeah.
No, it's not. Yes, it is. No, we know the date. No, we don't.
Yeah, yeah,
This constant.
yeah.
Forth.
Yeah, these are the cultural undercurrents that define a lot of this discussion. I mean, I think that a lot of people too are playing into these divides without even realizing it too. A lot of it is just inherited authority. You know, by the time that you have a PhD in astrophysics, you've kind of inherited a story that you've heard so many times from so many people you respect that it just becomes bedrock truth to you. It's a very strange time for science, actually, in terms of how you read you read people discussing ideas from the 1800s, 1700s, and they have a really open mindset for entertaining crazy ideas, right? So you read these, we're going to get into this next semester too for you guys who are here, but they're talking about what the sun is made out of back in the 17 and 1800s. And I mean, people are throwing out crazy ideas, but you know, they don't have this same sort of reaction to each other, like, oh, that guy's a crank or a pseudoscientist or an idiot or all this stuff. They're like very much like, well, Mr. Herschel's idea that there are Solarians living beneath the sunspots is intriguing, but I think that the infrared radiation would actually prevent that from being a possibility. But Herschel has good ideas about this, that, and the other thing, right? It's a very civilized discourse compared to today, and I think that tolerance for really far out stuff without throwing people wholesale under the bus led the science to progress much quicker than today. What's that?
I blame the internet.
Yeah, well, it's very interesting. I mean, today also science has become um, it's become a very state-sponsored event. It wasn't back then. It was very much a private sort of, what's the closest thing to it? I don't want to say it was a hobbyist kind of thing. There was still some academic components to it, but it was very much something that, you know, gentlemen and gentle ladies did. You know, they're mostly already rich people who were just kind of doing something that they considered to be intellectually esteemed, right? It wasn't like today where you had a job and your job was to be scientist. Like that didn't exist until the 1950s, basically. And because of that, now that everybody's career is tied up in it, and they're climbing ladders, and it's a very different world. And I think that you know, while technology has really just been chugging along, that method works really well for technology. It doesn't seem to have been so great for for theory, what we do in this class, which is really trying to come up with rational stories that match the data really nicely. The new kind of science has a tendency to sort of just bow down to the authority of the ideas that you inherit as far as the theory landscape goes. And so, yeah, you know, the modern world's great for building gadgets, but the science seems to have kind of stalled a little bit. Yeah.
Uh, you, I want to point out, aside from some terms, you almost what you generally just said is basically a quote from one of the Renaissance age natural philosophers discussing the change from the old order to the new one.
Yeah,
Right?
yeah, for sure.
Because there was the change between the uh, respect to the authority of the popes.
Yeah, of course.
During the
Yeah,
Protestant
yeah.
Reformation.
It's not so different, yeah.
Authority of the Pope. Respect the authority of the elders.
Yeah.
The Ptolemaic, people.
Yeah, yeah.
And this new age of, well, maybe they were wrong.
Yeah. Well, it's not a very smart career move to to think maybe they were wrong. Like, I think people misunderstand the way that science works a little bit today. It's like, if you want to have a good career in science, so you want to go to a nice university. Like, if I had wanted to stay in the ladder that I was on and keep climbing it when I was back working in research science, what you want to do is pick out a sort of topic that seems like it has some more details to be figured out. You want to find a topic that's well funded, so it's technologically applicable, in other words, right? Because you need to get grants in order to pay for your expensive experiments. You want it to be kind of promising, so it's safe, right? The last thing on earth you want to do is go into some theoretical space that has no ties to technology, where you think everybody has been wrong before you. That is literally like the worst, especially if you have a wife and children and stuff. Like, that's the absolute last thing on earth you're gonna do. So I just think that incentive structures are quite opposed to making massive revisions to the theoretical landscape that you would inherit. It's just not, it doesn't really make sense for somebody to do that in a professional
It
capacity.
seems like the role of academia has changed in the sense it's moved away from this two people in a room comparing arguments together, and it's now, which was that sort of philosophical exercise of identifying a truth,
Yeah,
or at least something that approximates a truth.
hopefully through a dialogue, yeah.
We're in this sort of capitalist model where if it doesn't, your job as an academic is to produce a result.
Yeah. Yeah, well, yeah, or just educate the next generation of technicians to get, to build stuff that'll sell. Which is great. Like, I actually think technical educations are great. But I also think that people who know how to think are important if you want your civilization to survive beyond its, impending horizon. Like, and the only way you learn how to think is by comparing two ideas that are both attractive. So, all right, let's do that really quickly, and then let's see if we can synthesize something. And I honestly just want to hear from you guys at the end. I'm going to try to save some time, because I want to hear before we close this whole thing down, what do you think about these two stories that we're kind of comparing and contrasting, and I want to get some synthesis back from you guys. But let's go back in time really quick and evaluate this a little bit. So, I'll give you a kind of whirlwind history of how this has gone down, and then let's look at some future possibilities too, in a little bit more, let's say, rounded out manner than we have so far. We'll be more on the nose about it. So we're looking at Descartes right now. So Descartes was this French philosopher, and he was actually the first person to propose that there was even a origin to the solar system. This is in 1629. So right after the Galilean revolution, right? So right after people started realizing that there was a solar system, period, in the kind of configuration that we understand it to be. These two other philosophers, one of them being more of a mathematician than the other, named Kant, you've probably heard of him, and this other dude named Laplace, developed Descartes' ideas into something more closely approximating what we understand today. So Descartes had this worldview that was very close to an ether model. He saw all material, from atoms to planets to the stars, as these vortices of this background substance, which is very ether-like. He called it the plenum.
Can I clarify just something real quick?
Oh, please, yeah.
On the historical,
Yeah.
how new is this idea of like the atomic? Like, how new is this sort of particle model?
Well, it's really old, actually. Yeah, it's hard to say. So it was never popular. The first proposals in any, most people think that when we point to the ancient Greeks, we have like some of their books or something lying around. We don't, unfortunately. We have essentially Roman texts who let's say, retranscribed Greek texts, and so their provenance is a little bit dubious anyways. It's like this guy says, well, I wrote down a copy of Leucippus's treatise on atomics or something, and it's like, who knows if he did or not? This is maybe 500, 1,000 years later or something. So is it legit? But basically, we have these second, third-hand telephone copies of these Greek texts. The concept of atomism seems to have been in play in classical Greece, so around 500 BC or something like that. Very unpopular, though. Very unpopular. So Greece was a kind of awesome place, by the way. I was just there this summer, and I think that it was very similar to the United States in that it was naturally laid out to have all these little island city-states, basically. So all of them had their own universities, for lack of a better word, on them. And they each had their own kind of philosophical schools of thought, and so you had a lot of competition amongst ideas. So the atomists were one little school of thought, and they figured that reality was sort of made out of chunks of stuff. That's really all they meant by atomism. They're like, there's stuff, all the stuff we see is made out of little smaller chunks of stuff. That was about as far as it went. And actually the oldest reference to it is from a poem by this guy named Democritus. But there's lots of, you can imagine that it was getting discussed quite a bit. But anyways, it gets lost, by the way. So we talk, the Dark Ages are called dark for a reason. So the Romans flirt with, there's some discussion of atomism. I found it mentioned, does anybody know Marcus Aurelius and Meditations and stuff like that? That's a good one, you all should read it. He mentions atomism in passing at least once in that book. But yeah, it's basically forgotten about until the Renaissance people dig up some of these classical ideas for the first time. And then later the Enlightenment thinkers refine them into a method, and yeah, they actually take this stuff seriously. So anyways, Descartes is one of those people. He's one of those borderline Renaissance Enlightenment thinkers. He actually makes a lot of headway in mathematics and philosophy, and starts thinking about the solar system and how it came to be the way that it was. And it was really the realm of philosophy for quite a long time. So the problem was that people more or less were attracted to. By the way, I didn't totally explain Laplace and Kant's idea, but the basic idea was that you have these giant clouds in space, and there was some evidence of this already in the way of these spiral nebula, right? So, which of course later turned out by the year 1900, people are sort of realizing these are actually probably other galaxies. And then eventually they built these huge telescopes and realized, yeah, these are definitely other galaxies. They start to be able to resolve individual stars inside of them. So these early astronomers, people with some of the first telescopes, they're starting to see these spiraling gaseous structures. They didn't know they were galaxies. They had no idea they were in a galaxy. They thought that the Milky Way was the entire universe until, into the early 20th century, which is pretty bananas. So they had this idea that, okay, there's this swirling dust or gas or something, the swirling, banking off of Descartes' idea of vortices, eventually condenses the matter, collects it, and refines it into the dense versions that we have today. Pretty standard. So, I mean, not too far off from the way we think about it today. Now, very early on in all of this, there appeared a really pernicious problem, which was what most of the history of dealing with this basic nebular collapse model revolved around. And that problem what is referred to as the angular momentum problem. So we've talked a little bit about angular momentum in this class. Does anybody remember the basic concept of angular momentum?
Yeah.
What do you got?
Oh, it's just like the further away you move from the circle, your velocity increases relative to your distance from the center.
Decreases, yeah. I mean, it's a conserved quantity. Physics is in love with these conserved quantities because it allows you to set up these equilibrium spaces where you can imagine how something unfolds from one condition to the next, all things being equal. Yeah.
Two examples that I hear. You brought up before the figure eight skater who, when they took their arms in, they.
Yeah, that's a great example. Yeah.
Another one,
Classic.
if you've ever done any form of racing in a oval, like on a track, you'll know that going on the inside of the oval, you cover less distance, so you travel that circle faster. When you're on the outside, you're traveling, even if you're at the same like acceleration, the same rate of like travel, you are traveling slower around the center because there's just more distance.
Yeah. So all right. So if we're imagining Laplace and Kant and Descartes' collapsing swirly stuff, um, well, just like the figure skater, as the mass that's swirling and collapsing gets tighter and tighter at the center, what happens? What should happen, anyways?
It should get faster.
The stuff at the center should be going really, really fast, right? Because that's how conservation of angular momentum works, right? The problem is that when you look at our solar system, and this hasn't been clear to you yet because we haven't studied the sun at all, but the sun is barely turning, is the truth of the matter. It takes something like a month for it to spin around on its axis. However,
I'm surprised with how big it is.
it's huge. So if you think of all of the mass of the solar system as being distributed throughout, radially, let's just think of it that way. Most of the mass is concentrated towards the center where the sun is. But that stuff isn't really turning very much. So there's very little angular momentum in the center of the solar system. And guess what? 99% of the angular momentum of the solar system is actually in the planets, particularly like 60% of it's in Jupiter. So Jupiter is actually both spinning really fast and it's also orbiting quite fast compared to the amount of angular momentum that the sun would be exhibiting relatively. So this is the kind of central crux of that bothered people for most of the history of this idea of how do you form a solar system. How do you make it such that your planets have all the angular momentum and your star has almost none of it, when basic conservation laws would tell you that a collapsing, swirling thingy should be exactly the opposite. All the angular momentum should be in the center. Very little should be remaining at the exterior. So people across the years, this particularly came to a head when academic science really picked up at the turn of the 20th century. People tried on lots and lots of different ways of solving this problem. And eventually, well, we'll talk about the favorite solution in a minute, but a lot of them involve two-body solutions. So, a passing star, right, would come by, and perhaps the planets actually arrived because as the passing star went by, our star ripped off a little piece of them, right? And so therefore, our star's angular momentum was a completely separate category of rotational energy than the planets that it scooped up, which their momentum corresponded to the star they came from, for instance, right? Which is actually, something worth holding in mind, that perhaps the angular momentum of the planets reflects their origin more than it does the star system they're associated with. It's an interesting idea. That one didn't hold for different reasons. Maybe not even so much that it was shot down as just that there was such a proliferation of variations on this theme. People were arguing that the planets would never survive a passing star, that the stars would never survive. That's a very famous one. So star collisions were advanced as a possibility for how to save the momentum. Again, same kind of two-body solution where your momentum of your planets is from a different system than the momentum of your star. What else? Another variation on this, Hoyle in the 40s proposed that perhaps a nearby star, a companion star, went nova, exploded, and that the planets were essentially captured from the material of that exploding star. Again, spares you the angular momentum problem. Hopefully you can start to see a theme. A lot of these have to do with a companion star, which is actually quite interesting. I don't think they realized this at the time of all these theories, but and we'll talk a lot more about this next semester, but we don't have a companion star, which is pretty bizarre. It's actually becoming more and more apparent that almost all stars have companion stars, but where's ours? We don't have one. It's pretty weird, actually. So
Seems like the more we discover, the more weird our solar system becomes.
exactly, yeah. I think that's why I think that's in some sense the exciting moment, just we're realizing, wait a second, all these stories we were trying to tell about solar systems in general were based on ours, and ours turns out to be a real odd man out kind of solar system. It's not particularly reflective of the rest of the solar system, and that's something we talked about last time when I showed you guys the different types of solar systems, most of them being self-similar with all the same types of planets, but certainly it seems like we don't even have the most common type of planet in our solar system at all. So what's up with that? It's pretty weird. There's all these little pieces that don't quite fit into the general solar system model about our solar system. What else? What are some other possibilities? Yeah, I mean, ve- mm,
We're still in this sort of like uh the ether model, right? When
the
we're
ether's kind of gone out of fashion by this point. So the ether went out of fashion around the turn of the 20th century. And most of these attempts to solve the angular momentum problem were in the 20th century.
So I guess my question is, if we were in this sort of ether model, whatever that paradigm dictates, you would have some material that is between the sun and all of these planets, right? So you would have some kind of actor that's connecting all of these bodies together, able to communicate information or energy
Yeah.
across that device.
Sure.
If we've left that etheric model, then there's nothing in there. So like if you had a material actor between them, according to what we understand on Earth, the sun could distribute the energy, that sort of kinetic energy, the angular momentum, to the orbit of the planets.
Yeah.
And then it would lose that energy, like a pool ball hitting another ball, and then it slows down.
I'm really glad you brought that up, because that is essentially the model that we've ended with today. Although instead of a material mediator of what holds us to the sun, right? I mean, as far as I'm concerned, the mystery of gravity, and for that matter, light and electricity and magnetism, hasn't really been solved, right? We have settled on the concept of fields, but when you push on the concept, it turns out the fields are really just maps of expected forces at the end of the day, like things that you would measure or feel as a result of putting a test charge at some location. Gravity is just a measure of what this body is going to do when next to another body, right? So we haven't really solved that problem. We just pretended like it's not a problem a little bit. So yes, that is essentially exactly how people have settled on solving this. So I'll tell you that story. Yeah.
Is it kind of like what we're seeing here with like this magnetic field clearly
Mhm.
visually? Magnetic fields don't have actual glowing lines that go. They don't actually.
That is true. I'm glad you realized that.
Visual.
Yeah, that would be nice if they did, yeah.
But whenever we
Especially if they were made out of stuff.
and atoms and how all these particles interact, it's basically that.
Yeah.
Saying that that's real.
Yeah, it's very strange. I mean, I could teach a whole class on the death of the ether. It's quite interesting. But needless to say, in the present technological era, it's more important to be able to describe how things will behave than it is to explain why they behave the way they do, right? So that's why we're so effective at describing, the way that a field would interact given some electrical or magnetic background, right? We can do that really, really well. But as far as like what the heck the field is actually pointing to happening, like what are the atoms doing to each other, or what are the actual bodies doing? It's just not a profitable question for people to ask.
Of our perception, though, too, right? Because the only thing we can even speculate about is we have to observe and conceptualize these things based on watching the actions,
Yeah.
consequences of those actions.
Yeah.
We can't usually see the things that are creating those actions or transmitting whatever that information is across these distances.
Yeah, it's invisible. I mean, but that doesn't mean that we couldn't nail it, because like the 2,500 years ago, some dudes on a Greek island were like, you know what? I think like that stuff's made out of littler stuff, and that turned out to be, I think a pretty obviously true answer. And to some extent, we can I hesitate to use the word see, but we're pretty confident in the idea that there are atoms that comprise molecules and that comprise tables and everything else, and human bodies for that matter. So it's possible, I think, to apprehend things that you can't see at the end of the day.
But through measurement, you can't observe it directly.
You can't observe it, you infer it, right?
You infer it.
So you look at your measurements, your fields,
Yeah.
because fields are basically maps of measurements. You look at your magnetic fields, and then you have to come up with a story like the atomists did, which is, why do things behave the way that they do? Why is it when I light this piece of wood on fire that it turns into this thing? And the atomists are like, well, it's just the atoms are separating and doing something else, and it's, it can all be understood in such a way. And it's crazy because they were basically right. I mean, the details of that are wildly complex, and I don't think they had any notion to the particulars of the chemical reactions or anything like that. But the basic broad strokes were dead on for people 2,500 years ago, almost 3,000 years ago. I mean, that's bananas, right? Just some guys like in togas sitting around just being like, yeah, I think that when this thing's on fire, like its atoms are just peeling off. And it's like, so yeah, we're awaiting some sort of revolution in terms of those kinds of ideas about what underpins the fields, and same for gravity as far as I'm concerned. But back to our story. I'm glad you pointed out what you did, because that's exactly how we explain away this angular momentum at present. So back in really all the way like through the late 50s through the 70s, there was a super prominent astrophysicist, this dude named Hannes Alfvén, who kind of he kind of rocked everybody's world by giving the astronomers a way to include electromagnetism in their model of the surface of the sun. And it ultimately led to people understanding as much as they do at present the solar wind and like prominences, the construction of flares and coronal loops and all the fun stuff we'll talk about in January. So he won a Nobel Prize for that. He came up with a science of describing it called magnetohydrodynamics, and we'll talk a lot about that next semester. But he also developed an entire preliminary cosmology based on electricity being the primary organizer of the cosmos, which is really wild. And there's a whole there's like a whole tradition of people devoted to Hannes Alfvén's ideas about that. Why do I bring him up? I bring him up because Hannes Alfvén he was already kind of an academic darling for solving the magnetohydrodynamics problem. And he basically provided a solution by which, in this nebular collapse disk,
What did you say? Electricity was the fundamental.
he calls it like a plasma cosmology, like electric. There's a group on the internet that was quite popular like 10 years ago called the Electric Universe, that are all devotees of Hannes Alfvén and his work. Yeah, there's a book that I read when I was a kid. I found it in the basement of the library called "The Big Bang Never Happened" by Eric Lerner. Yeah. I'd already read all of the normal books by then.
I missed the word you used, that's all.
What's that?
Because I missed the word you used.
Ah.
You said it's the fundamental, and then I missed the word.
Electricity. Yeah.
I know electricity, but what was the like?
Plasma cosmology?
No, there's a verb.
Magnetohydrodynamics?
No.
Oh God, what are we talking about?
Organizer.
Yes.
Yeah. The primary organizer is electricity and magnetism. Yeah.
Thank you.
That was kind of his shtick. And he used the same principles to describe essentially how the angular momentum could be transferred from the sun through these electromagnetic processes to the outer bodies in the solar system. And it was a very detailed technical mathematical argument for how it was that all of this angular momentum could end up in the outer spaces. We know that actually magnetism is really good at transferring momentum. That's what a transformer is. You guys ever have, like when you go plug something into the wall, those big heavy little box things that convert your AC to DC and all of that, they're just windings they're coiled wires, and they're literally transferring across an empty chasm the momentum from one coil to the next, right? So magnetism is really good at transmitting momentum like this, yeah.
Another way to see that is literally just when you have two magnets and one's spinning, and then you put another magnet toward it, and the magnet's going
Clicks off or whatever, yeah, exactly. Yeah, so it's actually quite, I think that people were jumping up and down that he'd solved this in a rational fashion for them, at least in theory, in principle. So, so great. So people for a while, so there's all these other models drifting around that I've kind of touched on so far. People are starting to build better telescopes. They're starting to see things that they see as that they might be able to construe as planetary disks, you know, things around stars that they consider might be young stars. All of this is really tangled up with the model for stellar evolution, which we haven't had any time for in this class. So it's all taken with a grain of salt. But it seems like the more that people are observing this, now they're becoming satisfied that the angular momentum problem can be dealt with the nebular collapse model. It starts to basically come back in vogue to the point that you know, all these other models for, you know, stars flinging off planets, that was a whole class I didn't totally get into. A lot of people played with that. I'm not going to get into that right now. But by the 1980s, basically everybody had returned to some version of the standard nebular disk collapse model. So, you know, just to make sure that we review, like we understand that model very well before we maybe explore alternatives. You basically have a huge, actually, it turns out that outer space, you know, the region beyond our solar system is full of stuff, actually. It's quite full of stuff. Not just simple gases, although there's a lot of that, but full of chemicals, molecules. There's really thick clouds, we call them molecular clouds, dust particles. All this stuff is essentially really good at condensing and forming little seeds. You can think of them as like a little dust, piece of dust is fantastic. It makes a template. Little ice crystals can grow on it. It can condense little droplets of stuff, for lack of a better word. And the idea is that all these little dust particles and molecules and stuff, that under the right circumstances, they will kind of slow down. Maybe they get hit with some sort of compression wave from a nearby supernova, but there's some sort of overdensity where you have too much stuff in one place. And at that point, gravity takes over and starts to kind of pull on the seeds of these things together. And then as the seeds come together, there's this, you know, really vorticular action, which is hydrodynamic in its nature. It's very similar to the way that swirling systems do in fluids. This gravity begins to pull on these things. They start to organize themselves due to this swirling process. And then, you know, this process not only makes stars, but it also, out of the same soup, is able to condense the cores of these planets. And the word condense it's appropriate at this phase because it's condensing these little pebbly things almost. And then gravity is somehow sticking these pebbles together. Once you get the little pebbles stuck together into some sort of boulder, then you have these boulders grow together into rocky planet type things. Once you have rocky planet type things, then they can grab a bunch of gas, or they grab a little bit of gas and they turn into a Neptune, or they grab a lot of gas really fast and they turn into a Jupiter. And then you have a solar system. I hope that I think that that's an accurate description of the standard stellar disk nebular collapse model. Okay, yeah.
While I was researching for my project, I found that they had confused a new object called a synestia, I believe is what it's called. Um,
Never heard of it.
yeah, synestia. It's a planetary object that basically um is this. It's a donut shape basically, where the center, the core, is very molten, but is condensed more
Hmm.
so, and the rest of it is more gas and liquid. Um, and basically, they found that they had confused early what they assumed were early solar systems for this, which is actually which is actually a planet
Yeah.
that probably got hit by something really
Oh, I
heavy,
see, I see.
and then it starts spinning really fast, and now it's shedding everything, and it's this big old field.
Yeah, I mean, we have to take a lot of these observations with a grain of salt, especially since all these exoplanetary things have been done in the last 10 to 15 years. I mean, many of them may turn out to not even be planets at all. And yeah, it's hard to know what you're looking at, but stick with me for a second. So I want to get some feedback from you guys. So I'm going to try to wrap this up in the next 10 minutes or so. Um, so that's basically the story that we have. Now, what sorts of problems can you imagine with that? I have one serious problem with it, but there's some other problems too.
How big are these boulders that are supposedly just magically?
Yeah, that's the worst part of it. For me, for sure, that's the worst part of it. Um, I do believe that someone who's a better mathematician than me could like dust the table with me with their mathematics about how you get pebbles to stick together into boulders, but it's um, it's a really, really serious just so story where you have to have this perfect kind of situation with this super thick gas that's kind of corralling your pebbles together. And yeah, it's just it's a very difficult argument. I believe that it's possible, at least I think that it can be argued mathematically, but it doesn't sit too well perhaps with everybody. Wait, hold on one sec. Yeah.
So for that, this would probably require extremely high density nebula for all of that to happen. Do we see that kind of density in any nebulas we can see out in the cosmos?
That's another problem. So when you get really thick dust and gas, you can't see inside of it. This is a huge problem because we don't really ever get to watch a star happen. We just assume that inside of this cloud thingy there is a star happening. And then we see stars that are of a certain temperature, color, whatever, and we say, oh, it's a young star because it fits onto our idea of how stars formed in the first place. So there's a lot of like confirmation bias associated with the stories that we tell about these things. So, I mean, there's other problems too. Like we've talked about. Hold on one second. So I want to make sure that I make it through this. We've talked about other problems, right? Why do some of the planets, our solar system's super diverse, right? Some of the planets are tilted this way and that. Some of the planets that seem like they should have magnetic fields don't have magnetic fields. Some of the moons that seem like they shouldn't have magnetic fields do have magnetic fields. Um, Things are very, very strange. Even the age of these exosolar systems don't seem to have anything to do with whether or not it has planets, the way that we're age dating these stars. So telling a cohesive story in this manner about something as diverse as our solar system is really, really challenging. The angular momentum problem notwithstanding, maybe Alphen solved it, maybe not. Yeah.
I was just gonna say one way you can have boulders smash together and become a bigger boulder
Mm.
is if they're
That's easier than pebbles sticking into
yeah,
boulders, by
but
the
if
way.
they're really hot.
Yeah.
If they're hot and they're more a little more closer to viscous than
Yeah.
solid,
Yeah.
yeah, they can
Boulders sticking together, maybe. The pebbles sticking together is easier if they're really cold and icy because they're kind of sticky, maybe. That's one of the arguments that's used. Um, I'm not saying it can't be done. I think it might be a possibility, but I think that there might be a more parsimonious possibility. So in general, like when we look at all of these solar systems, we really have like three things to consider. Uh, One is just these accretion models that we've been talking about for most of this class today. The other one is failed stars, brown dwarfs, Jupiter mass planets that are orbiting each other in star-forming regions. So transitions between, let's say, things that almost became stars but didn't. And I'm not even, well, maybe stars can also go the other way. That's going to open up a whole can of worms as well. And then we have relocation and metamorphic ideas to bring into it too. Is it possible that our solar system has planets that weren't originally part of our solar system? Or that some of the planets that were part of our solar system are now somewhere else and have joined some other party? These are, I think, directions in the future that'll be really interesting to explore. I want to throw one last crazy idea at you. This is actually, and we'll talk more about this next semester too, but this is actually an old Soviet idea from the 1970s. It originates in a book called Origin of Life by this guy named Oparin. But this guy, a friend of mine named Jeff Walensky, has developed this model. He's actually not a scientist at all either. He's like a former Marine who's now an arc welder, but he's devoted his life to this really old model, and he kind of discovered it independently on his own. There's also, if you want to read more about this, there's also a dude named Anthony Abruzzo who wrote a master's thesis on it at NYU back in the 90s, I think, or early 2000s, and that's about it. But the basic idea is that, and the way that Jeffrey kind of stumbled on this is he actually realized that if you look at the layered structure of an end-stage star in standard astrophysical textbooks, the layered nature of it actually looks very similar to the Earth in terms of there being kind of the heavyish iron nickel stuff on the inside, the oxygen levels, the silicons, all this stuff kind of layering outward. And he started digging into it deeper and deeper and deeper, and really came up with the idea that, like, and there's these three people throughout history have kind of come up with this same idea independently, which is, what if instead of stars when they die exploding all of the time, like our standard story would have it, what if they just sort of cool off over a really long time? What would they look like? And so, we've played with this a little bit. I mean, one thing is that they would probably initially look a lot like a brown dwarf or a Jupiter eventually. And if a Jupiter continued to evolve and cool off and dissipate, it would probably look like a Neptune. And if that cooled off and evolved, it would eventually end up looking something like an Earth. And what would happen if the Earth continued to age for billions, maybe, hundreds of billions of years? Well, it might look like a Mars or like a Venus or something. And what would happen if that aged and aged? Well, it might end up looking like a moon and so forth. So what these people are trying to do is actually put all of the astronomical bodies on one evolutionary timeline altogether. So that's a pretty far out idea. Now that's in stark contrast to the standard story of stellar evolution, which basically is told on this diagram that we'll get into next semester, which basically has stars, instead of cooling down the main sequence, like in this evolutionary model of planet formation, it has the stars moving off the main sequence. They basically get hot and explode at the end of their life. Or they get hot and nucleate at the beginning of their life, and then they join the main sequence for a while. They stay at the same place on the main sequence, which is just temperature versus brightness, and then they die. So that's sort of the main picture of that. So at the end of the day, I mean, I think that Walensky and Oparin and Abruzzo's idea is pretty extreme, basically that all of these bodies fit on an evolutionary timeline. But I also think it's pretty extreme that our standard model for biology is that all organisms fit on the exact same timeline too, right? It's like, that's a pretty extreme idea that all of us, everything that's alive, you and your cat and in trees outside, all go back to a single ancestor. And we all kind of accept that as being a bedrock fact at this point. May or may not be true. There may be multiple origins of life, and who knows what we'll discover in the future. But yeah, what I want to say about that is that, like, the stellar metamorphosis idea is an extreme version of an evolutionary theory. There's probably all sorts of soft intermediate versions of that, which I've kind of been kicking at you guys all semester long, right? Maybe in some cases, really what we're looking at with rocky planets is the evolved cores of these things. Maybe sometimes a huge droplet is on its way to becoming a star, but it doesn't have enough stuff to do it. And so it just, sits there and accretes and grabs up all sorts of metals and condenses them into cores over its lifetime. Maybe it eventually gets scooped up by a star system and becomes a Jupiter in that star system. There's a full range of possibilities that are sitting here. Yeah.
Just gonna ask if the guys who were talking about, did they have a model for how those systems came together to form a planetary model?
Well, in the stellar metamorphosis camp, which is the kind of the extreme evolutionary model, uh, they're all planets and moons and everything are dead stars, basically.
I think the question I was like,
Yeah.
well, then how do you end up with so many of those bodies orbiting a single evolutionary
Mm.
archetype of that,
Hmm.
and then maintaining stable orbits as they evolve?
A lot of time. So those timelines that those guys draw on are on the orders of trillions of years, so thousands of billions of years. So the Russians, by the way, they weren't drinking the Big Bang Kool-Aid at any point in time. They still aren't. So they weren't constrained in the same way we are in the West with the timelines so much, right?
Is the stellar metamorphosis model, is it derivative or directly related to the gaseous plasma model of stars? That is kind of is the
I don't. Yeah.
Does it sort of agnostic of?
Well, it can't be totally related because the standard gaseous plasma model of stars doesn't include the possibility that there's a solid core at the heart of them, right? And so the idea would be that Earth was basically at some point the solid core of a star of some shape, right? Again, that's a pretty extreme take on the evolutionary idea. I mean, we absolutely do see metamorphic pieces playing out in other star systems. So I don't know. What do you guys think? Let's try to synthesize something. I mean, this is the full range of possibilities. Ultimately, I don't know that. The fun thing about theory spaces is that you know from time to time one will become more popular than the other, but it's very difficult to say with any certainty about which one is actually true at the end of the day. Sort of, have to look at them very closely yourself and see which one sort of sings to you the sweetest. So, thoughts? What do you guys think? We got 8 minutes left. Any thoughts from the whole semester about this whole shebang? I mean, we've made it through the planets. I'm glad a few of you are going to stick around and learn about the stars because I think evaluating such a far out idea as this really requires you to understand the story of stars that we tell, which, spoiler alert, is missing some important pieces too. So, what do you think? Yeah.
I still can't get over. It was a couple classes like weeks ago when you showed the infrared photos of Jupiter and Saturn, and they looked like stars,
Yeah.
just like kind of a little different, basically
Yeah.
red dwarfs.
Yeah. I love that. All of the planets we see are reflecting light. So if you look in a telescope, you're seeing the sunlight bouncing off of them, right? But if you were to somehow screen out the sun, they would all still be glowing, actually. Now, they would be glowing brightest in the infrared, right? But there's a lot of radiation, more radiation coming off of, Saturn, for instance, almost twice as much than it receives from the sun. So they're radiating. It's not in a wavelength that your eyes really tuned to. It's a bit red. It's too red for your eyeballs, basically. But yeah, they're glowing. I mean, they really do. If you look in the right wavelength, they really do look quite star-like. I think it is at least easier to picture them on some sort of continuum that way.
But I just thought it was interesting that because if in the infrared it looks like a star, right? Then couldn't a star in a wavelength we can't see look like a gas giant?
Yes, the photos. Yeah, yeah.
And then
I mean, there are really interesting. We'll talk more. Let's get more deep into it next time because there's different. Actually, the closer and closer you look at this stuff, it's very hard to unsee it. There's differences in the convective surfaces of brown dwarfs versus Jupiters versus stars, but they do also fit really neatly onto a continuum as well. Yeah, yeah.
I still can't get over like how atoms they get charged and then they make stars and then they lose their charge and then they like die. And I like apply it to like a lot of things now, but like with the planet and how like it makes up the planets and then they have different charges, different things that like create life and then die and then more life. And I don't know, it's just like it's an interesting. Whoa, sorry.
Yeah, it's quite a cycle, huh?
Like continues to go, and it gives me like a perspective on our solar system.
Yeah. Yeah, it might be far more cyclical than we realize. You know, that's kind of the funny thing is that if these timelines expand, you know, you guys don't realize this, and we won't deal with it till next semester. But you know, these are thought to be the galaxy that we're in, and all of the galaxies that we see are thought to be the first galaxies that ever formed under the Standard Model. That could be completely incorrect. These could be this could be like the, you know, gazillion cycling of the basic material. This galaxy could have been a million other galaxies before, given enough time. It's a little bit trendy not to think so right now, but I certainly wouldn't write it off the table, you know. And so, yeah, maybe those cycles extend far, far, far back. You know, Nietzsche. You guys have to read Nietzsche in college anymore? Nope.
Depends on your track.
Okay, okay. So Nietzsche actually wrote about that. He was kind of driven mad by a lot of things, and one of them was, oh my God, like if eternity is a thing, then eventually the universe is going to run out of possibilities, and like I'm going to have to live my life all over again because the universe will make another one of me, right? He called this eternal recurrence, I think. So yeah, just how cyclic is everything? It's hard to say, but you know, given the space between 14 billion years and eternity, there's a lot of room for different outcomes there for sure. So, yeah.
I also think about how the larger we go up in scale and the smaller we go in scale, we tend to see mirrors, the
Yeah.
sort of thing.
Yeah.
You know, galaxies are kind of like solar systems in the way that they all these stars are orbiting this other, center
Yeah.
object.
Yeah.
There's and the galaxy.
Maybe a lot like atoms too. Yeah.
But then, there's all these little planets orbiting a sun, but then there's all these little moons orbiting a planet, all the planets as they orbit. It just seems this constant, like, and then you go away all the way down, and then you have like, the atoms and everything. It all just seems to be like this network of not
Self-similar.
but
Yeah.
similar stuff.
Yeah. It could drive you crazy. Watch out. It is true.
That's the hardest thing to get, I guess, to accept in a certain way, because when you start dealing with overly complex systems, you don't normally end up with ordered, repeatable systems very often. I think it's far more likely that a lot of the forces that we see, like with planetary formation and star formation, are the observations that we make of all of these different forces might just be the same expression of some very fundamental mechanical interaction.
Yeah. I agree.
At the smallest.
Yeah, it might be something quite simple, actually. Yeah.
And as it scales, we see these abstractions.
Yeah.
And
Yeah.
it creates these like
Yeah.
layers of complexity and turbulence
Yeah.
that complicate and
Yeah.
interact with each other.
I think you're right. Yeah. I actually think there's probably only one law, physical law, which is that you can't have two things in the same place at the same time. I think that's about all there is to it. And kind of everything flows downstream from that. It's a pretty simple reality that everyone's acquainted with. Anyways, I gotta let you guys go. It's been really fun to hang out with you guys this semester. And yeah, even if you're not in the class, stop by and say hi next semester. If you are, then we will continue this saga. Otherwise, yeah, you guys know your stuff's due. It's due on Saturday. I'll be grading it next week. But cool. I don't have anything else to say. Have a great break and see you around.
Thank you.
For sure. Yeah, for sure.
Yeah.